If you throw a ball straight across a spinning Earth, the ground curves away underneath it. Watch the yellow ball. From space, it travels along the straight dashed line. Clean. Boring. Meanwhile, the blue target rides east with the planet, and the ball misses it. Now ride along with the target. Same throw, same miss, except the ball's path looks curved. That apparent bend is the Coriolis effect, and the weird part is that nobody pushed the ball sideways. There is no little atmospheric hand reaching in from the edge of the screen. The curve appears because we insisted on watching from a surface that rotates while the ball is moving. Okay, that sounds suspiciously like wordplay. If the path is straight from space and curved from Earth, which path is real? Annoyingly, both descriptions work. They are measurements made in different frames, and the rotating frame needs an extra term to explain what it sees. Keep your eye on the pink observer standing beside the target. To her, the ball starts straight, drifts sideways, and lands somewhere it absolutely was not invited. We can reproduce that entire trick on a playground without using a planet, an atmosphere, or any scary equations. We only need a spinning disc, 2 people, and 1 throw that I got backward the first time I tried to sketch it. Shrink Earth into a carousel, and the mystery gets wonderfully cheap. Alice and Bob stand on opposite sides of a blue rotating disc. Alice rolls the yellow ball straight toward Bob. A camera bolted to the ceiling sees the ball move in a straight line while Bob rotates out of the way. Alice, rotating with the disc, sees the ball curl to her right. Bob blames Alice's aim. This is why Bob has stopped being invited to demonstrations. Now freeze the rotation halfway through. The ball keeps the sideways velocity it had at release. Alice keeps turning with the platform. Every moment, her idea of forwards rotates a little, so the unchanged velocity looks increasingly sideways in her coordinates. That is the first useful answer. The curve belongs to the rotating coordinate grid. We draw imaginary forces in that grid because imaginary is a slightly rude word here. The effect is measurable, and it predicts exactly where the ball lands. It is only the sideways pusher that is missing. Restart the disc twice as fast and the apparent curve gets stronger. Roll the ball faster so it crosses sooner, and the total deflection gets smaller because the platform has less time to turn beneath it. There is our first pair of clues. Rotation rate matters, and travel time matters. Earth rotates once per day, which sounds slow enough to ignore. Yet storms travel for days, ocean currents for months, and artillery shells can stay airborne long enough for surveyors to become extremely fussy. So how does this flat carousel become a globe where every point spins at a different speed? On the globe, the carousel changes size with latitude. A point on the equator travels around Earth's widest circle in one day, so it races east at roughly 1,670 kilometers per hour. Near the pole, the daily circle is tiny. Stand exactly on the pole, and your speed around Earth's axis is basically zero, though you do perform one extremely slow pirouette per day. Now launch our yellow parcel, north from the equator. It begins with the equator's large eastward speed. As it reaches narrower latitude circles, the ground beneath it moves east more slowly. The parcel keeps more eastward motion than the ground has, so it gets ahead. To someone standing on Earth, its path bends east, which is to the right of its northward motion in the northern hemisphere. Send a parcel south from near the pole, and the story flips locally. It starts with little eastward speed, arrives over faster moving ground, and falls behind to the west. That is still a deflection to the right of its direction of travel. I used to memorize north goes east and south goes west, which works until you turn the arrow around and your brain quietly leaves the building. The dependable rule is simpler. Moving objects deflect to the right in the northern hemisphere and to the left in the southern hemisphere. At the equator, that horizontal deflection fades to zero. Near the poles, it is strongest. This latitude dependence is the part most carousel explanations hide, and it sets up a very good problem. Can one compact formula predict the direction and strength without making us track every latitude circle by hand? The compact rule is hiding inside one cross product. Here is the only formula wall, and I promise it is a very short wall. In Earth's rotating frame, the Coriolis acceleration is negative 2 times omega cross v. Omega is Earth's rotation vector, pointing along the axis toward the North Pole. V is the object's velocity relative to the ground. The cross product produces a direction perpendicular to both. Honestly, the notation is ugly, and I apologize on behalf of everyone who decided a tiny multiplication sign should also encode a three-dimensional hand gesture. We can make it behave. Put a yellow velocity arrow pointing north on a patch of the northern hemisphere. Project Earth's blue rotation arrow onto the local vertical. Its size is omega times sine of latitude. Apply the cross-product direction and the pink acceleration points east to the traveler's right. Reverse the velocity and the pink arrow reverses too, remaining on the traveler's right. Cross the equator and the useful vertical component changes sign, so right becomes left. The horizontal deflection has magnitude 2 omega v sine phi. Faster motion gives a stronger instantaneous acceleration, even though a faster trip may accumulate less displacement because it ends sooner. That distinction tripped me up for a while. Stronger acceleration per second, fewer seconds available. Both can be true. Now hold this finished diagram for a beat. Blue omega, yellow velocity, pink Coriolis arrow, and the sign of latitude slider. This one picture predicts the carousel, the globe, and the hemisphere rule. It also predicts something enormous. If air begins flowing directly toward low pressure, Coriolis should turn it sideways. So why does a storm spin around its center instead of falling straight in? Air does start toward low pressure, then Earth makes it miss. Picture a low pressure center in the northern hemisphere. The pressure gradient force points inward. Give one parcel a small inward velocity, and Coriolis turns that motion to the right. The parcel accelerates inward, gains speed, turns more, and begins orbiting the low instead of taking the direct route. Add parcels around the circle, and you get counterclockwise flow. Around high pressure, the outward push and rightward deflection produce clockwise flow. In the southern hemisphere, swap those directions. This is the part weather maps quietly use every day. The wind often runs roughly along pressure contours because the inward pressure force and sideways Coriolis acceleration balance. Meteorologists call that geostrophic balance, which sounds like a mineral supplement. Near the ground, friction slows the wind. Slower wind means weaker Coriolis acceleration, so pressure wins a little and the air spirals inward across the contours. That is why surface winds can feed a storm, rather than circling forever like polite little satellites. Hurricanes make the rotation spectacular, though Coriolis does not provide their energy. Warm ocean water does that job. Coriolis organizes the moving air and helps set the spin. It is also weak near the equator, which is one reason tropical cyclones rarely form within about 5 degrees of it. Now our screenshot diagram has grown teeth. The same pink sideways arrow that nudged a carousel ball can organize weather systems hundreds of kilometers wide. But this is where people usually drag in toilets, sinks, and every bathtub they have ever watched. So, does Coriolis decide which way your drain spins? Usually no. Your sink is too small, drains too quickly, and contains enough leftover swirls to bully Coriolis completely. A slightly crooked basin, the direction you pulled the plug, even how you washed your hands can matter more. Those equator tourist demonstrations with neighboring north and south drains generally involve careful pouring and showmanship. Great theater, questionable geophysics. In a large symmetrical tank left undisturbed for many hours, Coriolis can influence the final rotation. The experiment is real. Your Tuesday night pasta water is not that experiment. Scale and time are the filters. The sideways acceleration is tiny, so it needs long travel, high precision, or huge moving system to become obvious. Long-range artillery crews account for it. So do missile guidance systems. Snipers may need it at extreme range, though wind usually arrives first and ruins everybody's clean textbook day. The famous Foucault pendulum reveals Earth's rotation through a related rotating frame effect. Its swing plane stays nearly fixed in space while the floor turns beneath it. Ocean currents are deflected and organized into vast gyres. Even satellites and aircraft navigation systems must keep their chosen reference frame straight, or the bookkeeping goes feral. Here is a useful smell test. If the motion lasts seconds across centimeters, local imperfections probably win. If it lasts hours across hundreds of kilometers, Earth has time to show its hand, and that finally lets us answer the opening without hiding behind perspective. The ball follows its free path, Earth rotates beneath it, and a surface observer uses Coriolis acceleration to predict the growing sideways miss. One detail is still loose though. We have only talked about sideways bending. Coriolis can also push vertically. That vertical piece is called the Eötvös Effect, because apparently one named effect was not enough. Move east with Earth's rotation, and you are circling the axis faster. Your required inward centripetal acceleration changes, so in the rotating description you feel slightly lighter. Move west and you feel slightly heavier. Aircraft and precise gravimeters can measure this. The change is tiny, yet it comes from the same cross product we just used for storms. Turn the velocity arrow east, and part of the pink Coriolis arrow points upward. Turn west, and it points downward. So the full picture is stranger than the familiar right in the north rule. That shortcut describes horizontal motion on the surface. The three-dimensional rule cares about the rotation axis, your velocity, and their cross product. Nothing in it knows what a weather map is. Nothing says the force must stay flat. Zoom all the way back out now. The yellow ball still travels cleanly through space. Beneath it, every blue latitude circle carries its observer in a different direction at a different speed. Each observer draws coordinates on moving ground, measures the miss, and gets the same answer from -2 omega cross v. That is the magic trick. The curved trail is a record of the observer turning while the object travels. And here is the thing that still bugs me. Even though the math checks out, standing on Earth feels like the neutral viewpoint. It feels like the floor gets to define straight. Then one patient pendulum, one storm, or one badly aimed yellow ball reminds you that the floor has been moving the entire time.